Okay, good morning. I think, is it still morning? Just barely. I'm Jeremy. I'm from Sandia National Labs. It's in Albuquerque, New Mexico. I am the manager who drew the short straw. So I'm up here to tell you about the work of a lot of other people, some of whom, or many of whom, are here today. So if you have more questions or want to dig into the details or find out all the ways in which I misspoke and misrepresented their work, talk to them. Okay, I have a organizational responsibility for a group who does modeling and simulation, as well as a lot of soft materials development and advanced manufacturing processes, but also programmatic responsibility for production simulation activities within one of our advanced scientific computing programs at the lab. So, okay, if you're not familiar with Sandia National Labs, perhaps you're familiar with Los Alamos National Labs or perhaps the Manhattan Project. That's our genesis. We've just celebrated our 75th anniversary. We are an FFRDC, a federally funded research and development center. So basically what that means is contractor, government-owned but contractor-operated. INTES, wholly owned subsidiary of Honeywell, has the contract to run Sandia currently. And as an FFRDC, basically our job is to be long-term strategic partners with the federal government, and we operate in the public interest with objectivity and independence and maintaining some core competencies in missions of national significance. Obviously, the strategic nuclear deterrence is our genesis, but we have a number of missions across national security areas these days. And one in particular that's relevant to the crew here is advanced science and technology, especially computational and advanced manufacturing technology. But Sandia has made contributions in the area. I mean, as an FFRDC within the ND mission space, we are a design agency and a system integrator, but we have much broader impact in other missions, even in energy security. So we've made contributions in fuel cell technology and helped field the first fuel cell powered ferry. Also wind turbine design, more efficient wind turbine design, unmanned vehicle sensing technology. In the manufacturing space, we pioneered clean room technology quite a long time ago, which enabled much of what we're talking about today. We have a long history in high-performance computing, both software and architecture, and large-scale, high-powered modeling and simulation activities that sort of goes all the way back to those early days around precision microelectronics fabrication. But in terms of the other impacts that we've had in the manufacturing space, actually for advanced or additive manufacturing, Sandia has had 30-plus years of technology development and commercialization. So you've seen a lot of those represented today, from anything from what we used to call robocasting. Nowadays, we call it direct ink write, so extrusion-based processes of soft materials like polymers, pastes, inks, those kinds of things, whether they end up being fired and made hard like ceramics, or pads and cushions and encapsulants. Also lens processes, laser engineered net shaping, I think is what that refers to, and thermal spray processes, just to name a few. So Sandia has been involved in this space for quite a while and developed some seminal technologies in the additive manufacturing space. More relevant to this talk right now is our activities in the computational space. So historically, we've developed a number of tools within the advanced simulation and computing program, focused mainly on qualification activities, detailed, high-fidelity physics, high-performance calculations to understand the function of systems and components, as well as to quantify whether they will perform, or qualify whether they will perform as intended. So that's kind of our history. In more recent time, we've moved sort of to the left. If you think of the qualification activities on the move to the right. On the far left are the qualification activities centered around our Sierra tool suite, which is a finite element tool suite that houses everything from thermal fluids analysis to solid mechanics and structural dynamics, aeromechanics, as well as a lot of underlying foundational computational technologies. That's sort of been in the qualification space. Moving all the way to the right, more recently, with the development of the Plato tool suite, we've moved into a design optimization and orchestrating workflows around gradient-based optimization processes, topology optimization, shape optimization. And those are two of the things that I'll talk to you about today, some of those tools, Plato being open source and other open source tools that we use as well. But more recently, we're trying to integrate across the entire workflow to bring about both a design to qualification centered around the actual production process, manufacturing activities, a full digital workflow of our computational, integrated computational capabilities. So, and then trying to instantiate that, not a very good projection up here, instantiate that in something like a product realization workflow. Okay, so looking at the manufacturing activities that we have in the computational domain, a simple sort of step through of how we might go from an idea to a product, we could lay out in a nice linear box diagram like this, just to highlight some of the activities and some of the tools. So there might be some idea for a part or some design that we might want to optimize. Maybe that's a topology optimization type process. But we're not necessarily limited to that. A typical additive manufacturing, you are kind of, you're building the material at the same time you're building the part, and that has its challenges, especially when it comes to variability in the process and uncertainties that brings into the actual material structure and the material properties and then the performance of that material. One of the things we would like to do is sort of invert the current state of technology, which is you live with what you print. We would rather print what we want. So using the fact that we're making the microstructure at the same time we're making the part, can we tailor that microstructure in some way that enhances the function or optimizes the performance in particular regions of interest? Then we might want to take that design, which is pushed both topology optimized, let's say, in an ideal world at the part scale, all the way down to microstructure, and make it process aware. So actually, now that we have a part, simulate the manufacturing process and optimize that process to minimize maybe residual stresses or distortions subject to some engineering requirements. And then at some point in the process, there's a handoff between what has been talked about so far as a computational virtual workflow to the actual physical process of making the part. But that in itself as well has become very digitized in terms of the tools and the techniques and how they function, as well as the sensing and the in situ monitoring that can be tracked and analyzed. And at some point, we need to fuse these two things in the digital world, the physical part and all of the information and data that we can collect about the process and the materials and the part as it's being built with our virtual predictions, so that on the one side, we might have the physical part and running in real time, either as a check or perhaps in a closed loop setting, being able to monitor that process, correct that process, or inform our calculations as a result. So really at the core of what we're trying to get at when we integrate these computational tools is a level to design both at the part and microstructure scale that's process aware and then integrated digitally with all of the information that we can extract from the actual process as the part is being manufactured. So with that as a backdrop, I'll talk a little bit of about some of the computational tools that we use at different phases of these workflows. So the first one I mentioned was Plato. Plato is really a tool suite for integration and orchestration of optimization-based analyses, particularly shape and topology optimization. Plato, at its core, has its own physics analysis engine which is highly optimized and built around automatic differentiation, which exposes those gradients and derivatives of key properties for gradient-based optimization and orchestrates all those workflows. In addition, Plato can also interface with our favorite finite element analysis tools, which we've spent a long time developing and making very robust and very performant in terms of the high-performance computing architectures, as well as validated material models, our Sierra tool suite. So Plato is able to integrate with all of these and sort of orchestrate these workflows for some key sort of bread and butter activities. One of those, as I already mentioned, centered around topology optimization, but there's a lot of, and shape optimization, but there's a lot of other research activities that are going on in this space around this tool suite. And I'll go into those a little bit, but one of the items that I want to point out is optimization under uncertainty. So if you have very well-known and well-described loadings, you might take a structure such as what's shown in the center here and optimize to a very nice, neat, almost elegant geometry. But if there's any uncertainty around those loadings, you might need to build in some robustness. And so some of the research activities in the past have centered around optimization under uncertainty using Plato. More recently, however, there have been a couple activities I mentioned already, the process-aware design for AM. So the movie down there in the lower left is optimization of the stiffness of this part. At the same time, you're trying to minimize the residual stress as it's being built up in a laser powder bed metal AM process. So controlling the heat and the stresses that build up in the layer as you're at the same time you're optimizing for the stiffness of that part. So this is one example of sort of bringing these computational tools and to multi-objective optimization to a process-aware situation for metal AM activities. Another optimization example here is around cellular design. So if you have a lattice structure, and this is where 3MF comes into play. So topology optimized design, it's based on a homogenization approach, but there's a way of mapping carefully between the homogenized continuum method that's being used to do, again, a multi-objective optimization here. Shear forces and thermal gradients on this double-ringed sort of structure, which is printed actually and over on the table if you want to take a look at it. So multi-objective optimization for this lattice structure. I think Josh Robbins is responsible for this work. He was just telling me during the break that 3 orders of magnitude is a reduction in file size for to go to from a STL representation to the 3MF representation for this particular geometry. So a significant advantage with going with that file formatting capability. Loaded easily. Brandon told me it loaded easily into the machine, and we're able to print it. Ti64, I believe, is what the metal one is sitting over there pretty seamlessly. So powerful tools for lattice structures and process-aware optimization. Other emergent activities in this space really have to do with nonlinear mechanics and non-equilibrium mechanics. So if you want to optimize for these foam or lattice-like structures for soft materials, you want to optimize energy minimization or stiffness or these snap-through sort of geometries, which are kind of neat and cute for various applications. Again, the tools that are being developed in the Plato suite, or again, dynamics, if you're interested in the modal response of parts and you want to optimize those modal response for structural behaviors. Again, these nonlinear capabilities and solvers that are being built into Plato are handy for that. Again, open source package. Okay. So moving on from Plato, going back to Sierra. So Sierra, as I said, was a finite element package that handles a lot of the thermal fluids capability, as well as structural mechanics, structural dynamics, very robust, highly performant. And we're developing very detailed melt pool models and validating those models against physically realizable processes and materials. And then upscaling, quantifying uncertainty and the predictions of those models based on machine uncertainty for, pick your favorite metal AM, let's say, machine, and understand what the variabilities of the laser scan speed and power and all those fun things are, and propagate uncertainty all the way through the full physics weld pool and understand what is the variability, and do your simulations fall within or bound the experimental variability that you might expect. So coupling these full physics models with full verification and validation and uncertainty quantification, so that we can then scale up to sort of laser scan strategy and optimization procedures to do more detailed and more rigorous residual stress and distortion compensation activities, as well as predictions for microstructure and the design of scan strategies to get specific types of microstructure in specific locations. So coupling these activities from the melt pool scale to the part scale, thermal, fluid, mechanical, microstructural, and passing uncertainties through all of these modeling and simulation is something that we're very keen on and have spent a lot of time developing that rigor to be able to do that. Okay, direct ink write is another application. So you see a movie here for lattice cushions and pads where you're crushing kind of like foam or encapsulant. Standard workflow might be you come up with some kind of geometry, then you slice that and print that, and then you test it. Does it give me the response that I want? And you iterate on that. We're developing computational workflows based on our tools, both meshing and geometry representation, and our finite element analysis tools to automate that, to explore virtually what is the optimal or what are the different lattice structures, and build up the library from a computational perspective, and then export those directly to the printer, as opposed and optimize that sort of design loop on the virtual side before we actually go and print. We're also developing the computational tools to model the printing process itself for, again, defect detection, in situ process monitoring, and production optimization as well. Some newer capabilities that we're just starting to get up to speed, also at like the lattice cellular structure, sort of mesoscale. These are at powder scale simulations. Again, the resolution is not great in the projector, but what you would see here is individual powder particles resolved for something like a binder jet or other processes that are centering based. We really want to understand how the part is shrinking, and the burnout process happens at the sort of powder scale, to be able to predict that and control that using our open source, actually molecular dynamics code, but it has a granular powder modeling lamps package to be able to develop these tools for these types of processes. Finally, what we'd like to do, as I said, is kind of take all this capability in terms of validated and verified, uncertainty quantified, part scale, process scale, microstructural scale, in situ diagnostics and monitoring, and bring that all together into a framework that allows us perhaps a generative design kind of an approach, or at a minimum some in situ process monitoring, defect detection, and perhaps feed forward control and automation of the processes of themselves. So for us, generating tons of this data and operating on this data is something that within the high-performance computing activities at Sandia is something we are very keen on doing and have the capabilities to do. So in the end, again, hopefully you got a taste for some of the physics-based modeling and simulation tools that we're advancing, and sort of these credible simulation approaches. We're integrating them at part design and process optimization scales for CDFAM. They're multi-scale from meso and microstructure. Also, the validation and verification of these capabilities is robust, along with the uncertainty quantification and uncertainty propagation through the coupling of these different methods is something that we have an expertise in. Going forward, ultimately, what we'd like to do is develop approaches for digital integration of these mod-sim workflows with the in-situ data collection activities. And this is something that we'd like to do for the ability to have sort of on-machine inspection and born qualified parts, and ultimately to accelerate our product delivery time cycles. So with that, thank you for your time. Appreciate it.